2011 North American School of Information Theory, Summer School of Information Theory. I don't know which one it is, but one of those two, right? In Austin, Texas. It is a summer school, and if you were to step out at about 4 o'clock today, you'll notice it's summer. But welcome to Austin. It's a beautiful town, and we're very glad to have all of you here. Before I go any further, we have to thank our I need to close my Skype. Anyway. There we go. All right. So, actually, is everybody able to see this without any issues? Before I go ahead? Because I feel it's a little bit out of focus. We'll try to fix that if there's an issue with that. Is it okay? Okay. So, we have 5 very distinguished speakers. This time we're going for a format of 3 days where we have the IT school, and on the last day we're going to do something very funky and fun. So I'll talk about what the last day is in a little bit, but very kindly they have agreed, some from very far away, to come all the way to the University of Texas and to talk to you, meet you. So let's give them a warm welcome. At the moment we have 3 of our speakers here. The 4th one should be here hopefully shortly, and unfortunately the 5th one is at ICASP, and he's going to join us on Saturday. So that we should have everybody here, at least definitely doing the talk, but at least for a little bit of duration for you to interact with them. So the basic idea is for you to get to talk to them, interact with them, ask them questions, about their talk, about their general research, about life, and PhD or anything of that sort. Anyway, so thank you very much. Couple of things. There is a social event every evening from Friday through Sunday. So a simple dinner, it won't be anything sophisticated, will be provided with the event. So for example, on Saturday and Sunday it's pizza. And I apologize for that, but that's what goes with movies and popcorn, I guess. But pizza and then bowling are for Saturday and Sunday. And Friday we have a poolside party. We wanted you to socialize outdoors and get to know each other. Movie nights are not that sociable, so I'm hoping you'll get to know each other on Friday, enjoy a movie on Saturday. A poll for the movie went out with the emails. I hope you've voted. If you haven't, please vote, and we'll hopefully pick the movie that you like best. All right, there should be internet logins in your packet. I apologize if it is not there. We're in the process of fixing it. And the parking, because it's break time, you should be able to park anywhere on campus after 5:45 today. Not anywhere, most places on campus, unless it says reserved all times, until Monday night. So if you are, Samantha just joined us, so we have 4 of our 5 distinguished speakers here. If you need to park, please park anywhere on campus. If you need a parking permit or any parking discussion, please come see me. I'll be happy to make arrangements. Also internet login and name tags. If we're missing name tags, then by noon, hopefully I'll have that fixed. All right. A couple of things continue. If you're a member of IT Society, you get $30 off on your dorm fees. Okay? If you are not staying in a dorm, unfortunately you don't get anything off, because that's the only fee that we have, all right? So if Jennifer is going to be here over lunch. She is the very able admin who has dealt with everything. In spite of my follies and mistakes, she has managed to fix everything. So I'm glad all of you made it here, by the way. It's thanks to her. So she will be arranging your $30 off. If you haven't, an ITSOC member, want to become ITSOC member, can register online right now or something, you get $30 off. So please do that, and we can make arrangements for you, $30 off. You'll get it post-checked in the mail. All right? Let me know if you haven't done it already. Today lunch, we want to take care of it. Okay. So Monday is an exciting day. We have Rudy and we have Alon, who are teaming together to put together a show all of Monday. So from, I want to say after breakfast till 5 p.m., they are talking to you about creating a Wikipedia for information theory. Okay? So you are all going to be working in teams, or perhaps even individually, creating wiki pages on everything from entropy to whatever else is your favorite information theory concept, right? So we will be, and that's part of the theme. There's also a little show and everything. I want to find out how many of you can stay till 5 that day? Show of hands. At least the locals, I hope. That's not bad. Please continue so I can get a count. That's a good number. How many of you can stay till noon at least? Maybe even beyond that, including those who said 5, so I get it overall. Yeah, that's a good number. Okay, so if I would really, if I can, convince you to stay till as long as you can stay. The airport is only half an hour away, right? Check out, stay for as long as you can stay. If you're looking for Monday night dorm room arrangements, I'd sent an email out on that. We can still get with housing and try to make that happen, right? So, but it's, I know this was a last minute thing, so if you're not staying Monday, it makes sense, but if you are staying, great. I think we'll have a fun, and Rudy and Alan can be a lot of fun, so it'll be a great time. All right. So, last but very important, our sponsors, without whom we can't do anything. We have the IT Society, which has put in more money than ever before. They're our platinum sponsor or equivalent. And then we have the Army Research Office, the university systems in Texas, University of Texas, Texas A&M, and Rice University. And today's lunch is sponsored by the new Science of Information Center. If you haven't heard about it, you're going to find out over lunch. There'll be flyers and everything put up by the Science of Information Center. So they're sponsoring lunch today. And Princeton University is our last sponsor. So thank you very much. If there are no questions, I'm going to introduce Emre. Any questions? Okay. Well, we're running late, so we should start. It's my pleasure, absolute pleasure, to introduce Professor Telatar. He's visiting us from the École Polytechnique Fédérale d'Ossal. My French is not very good, but EPFL, and he has, most of you would know his work, in fact all of you I presume would know his work on MIMO. It's in the mid-90s, in fact we can predate that, but he has won the IT Society Best Paper Award in 2001. He has multiple honors, but what makes him exceedingly a good teacher is he's both very knowledgeable and very easy and approachable. So it's a pleasure, real pleasure to have him come all the way from Europe to come speak with us. Emre, thank you for coming, and we look forward to that.
Well, thank you very much indeed. It's great to be here in Austin. I was here last year for the Information Theory Symposium, and I was very surprised by how un-Texan the place was. I was expecting desert and dirt roads, etc. And when I come here, it's green, wet, and very pleasant. It's very nice to be here. Thank you very much for inviting me. I'm glad to be here. I only have actually one slide, I think, but let me show it. I may use a computer for the purposes of... actually, I will use a computer for doing some numerical experiments and plotting and so on and so forth, but... maybe it's not in my place to do this, but I sort of feel that I should. We lost Jack Wolf 2 weeks ago. He passed away May 12th, 2 weeks ago yesterday. Well, Jack is, of course, he's a brilliant scientist. I cannot really need to elaborate any more about that. But he was also one of the kindest people I knew. So he's very gentle people. And even in our society, I think society is actually maybe blessed with an abundance of gentle people. I think the founding generation of our society consists of people who are not just brilliant, but they're also really nice guys. Okay? You go and speak to any one of these people, you realize that these people really care about you and the society and many things. And Jack, even among that group, was, I think, exceptional. So I think we're a bit poor without him, so I just wanted to say this at the beginning. I think it's the first time I try to say such words. I apologize for any awkwardness, but I thought I should say something. That's the only slide I had, so maybe on to more pleasant business. Perhaps I should raise these. Have you seen that I have a jacket, by the way? It's a trick I learned from Bob Gallagher, so this is to show up that you have something, and then got the tie also, but no more. All right. So today I want to talk about something called polar codes, or sometimes called polarization codes. So these are error correction codes for how to transmit information over a noisy channel. Okay, these are for the binary channel. So these guys are provably capacity achieving. Okay, so and they have low complexity, and they have one more advantage in the I'm not their inventor, so this actually makes me be able to say very good things about them without being embarrassed. Okay, so they're invented by a good friend and colleague, Telatar, who won the IT Society Paper Award for this in when was it, 2010? I guess it's not presented yet. And what I want to do is to explain what these things are, why they do what I claimed that they do, and how to perhaps construct them. I hope I'll have enough time to do all these things. As I said, these are low complexity and probably capacity. Should be capacity quotation marks because it will be something that what is called symmetric capacity. I'll tell you what these things are in a moment. Maybe I should start by the following thing. So first of all, polar codes, when Erdal first described it, he talked about a phenomenon of polarization. So many people who heard polarization, they thought, this must be something to do with electromagnetics, some sort of antennas, propagation, etc. It has nothing to do with any of those. Okay? So it has more to do with polarization, say in the terms of the society being polarized, for example, between rich and the poor, or yin and the yang, good and evil, Republican, Democrat, take your pick as to opposing entities. So I'll tell you what are the polar opposites in this context are. They're the following. So after all these years of information theory, there are two channels which are very easy to communicate over. Okay? So optimal to communicate over. So two extreme channels. So one of these is the perfect channel. Okay? So I'm going to talk only about, by the way, binary input channels. Okay? So one of the channels is this one. You send a 0 or a 1 at the input. What you receive from 0, so these are the set of possible observations at the output of the channel if 0 is sent. Okay? And these are the set of possible observations at the output of the channel when 1 is sent. And these are disjoints. Okay? So this is a perfect channel. So when you see the output, you know exactly what was sent. Okay? So if the output falls into to this bunch of output symbols, you know for sure that the 0 was sent. If the output falls into these bunch of output symbols, then you know that the 1 was sent. So it's a perfect channel. we know what to do for this channel. You simply send uncoded information. You don't need to do anything, no coding necessary. Take your raw data bits, push them across the channel. You'll be doing optimal decoding. Okay? This is capacity 1. So this is the perfect channel. The other channel is the following. It's a channel for which the output contains no information about the input. Okay? So it's the following thing. So take a look at the channel. W is the transition probability of this channel. W of y given 0 is the same as W of y given 1. Okay? So the statistics of the output do not depend on what symbol that you're trying to send. Okay? Hence, this is a completely useless channel. Okay? It's also very easy to communicate optimally over, because the optimal communication rate of the channel is 0. So you can simply send no information and you'll be doing perfectly good. Okay? You're doing as well as you could do for this channel if you were simply sending a constant, for example, for this channel. Okay? So this is the junk. Okay? The perfect channel versus the junk channel. So the polarization will refer to the following phenomenon. We're going to take any given channel and then convert it into some collection of the perfect and the junk. Okay? And we're going to do this in a way in which no total information is lost. Okay? So we're going to essentially decompose our channel into these extremal channels. Once we have done that, the communication problem will become very easy, because we know what to do on this case, we know what to do in this case. Okay? In both these cases, you notice that coding is not necessary. Okay? So the coding problem will be solved by this decomposition, which itself is going to be coding, of course. The polar code refers to this process of decomposing a particular channel, neither yin nor yang, okay, into the extremal yin-yang channels. Okay? So yang-yin, depending on your preferences to which one. All right, good. So now, maybe I should say one more thing about these polar codes, which is the following. If you take a look at the beginnings of information theory, the people who were doing information theory and the people who were doing coding theory were the same. Okay? So if you take a look at, let's take Bob Gallagher as an example. Okay? So I think of him as being an information theorist in the pure sense. But if you look at what he has done for his PhD thesis, it's, serious coding theory of the PC codes. So at that epoch, the two theories were really intertwined, okay, and people understood both. Okay, so and then the techniques that were used in one were also useful in the other. Over the years, I think the Shannon theorists, I guess I consider myself among that community. We sort of became enamored with things like random coding arguments, existence proofs, converses, etc., typicality arguments, and so on, to show what can be done in principle and what cannot be done in principle, okay? And less concerned with how these things are supposed to be done. Whereas the coding theorists, they became more enamored with finding structures that you can use to communicate or compress and so on, so they became very involved in combinatorial structures, algebraic structures, etc. And the two communities diverge from each other. Now we're seeing, I think, in the recent years, particularly with the Trudeau codes and LDPC codes, and now with the polar codes, that in fact the techniques from one and the other are again becoming useful to each other. Okay. In this particular instance, we see this polar codes have a very strong sort of probabilistic construction flavor, which is like random coding like, but at the same time they're solving a coding theory problem, so it also is nice that that these guys begin to form bridges between the somewhat standard communities. Okay. People might disagree with my comments, by the way, so even I might disagree with myself in the next hour. By the way, stop me any time. I haven't said anything useful at the moment, I realize, but when things get going, do let me know. But I think, however, it's clear what I mean by the perfect and the junk channels. I hope that is clear for the time. Okay, so here is what. So here's what we will do. Okay. So let me try to explain how this polarization process will happen. So we'll be given a channel W. Okay. Here's W. It is an input. Okay. It is an output here. The input is binary. Output anything you like it to be. So I make no restriction on the output alphabet. It could be pineapple, banana, orange, real numbers, whatever. So I'm going to take 2 copies of this. So of course you can obtain 2 copies of your channel. Means that you are designing a code block that is 2. Right? You use the channel 2 times. If you think of the time domain, these are 2 successive uses of the channel. Right? They will of course represent maybe different frequencies, etc. But whatever. So you have 2 uses of this channel. These are going to be independent uses. So it's a member of this channel. So the 2 successive uses, they are independent of each other. The following. I call this, let's say, x1 and x2 as the input to this channel. What I'm going to do is a completely trivial code. Okay? So namely, u1, u2 are going to be my message symbols. You're going to form x1 by doing u1 plus u2 is going to form x1, and x2 will be equal to u2. Okay? So, and all these plus signs are modulo 2. Okay? So when I say plus, it is 1 plus 1 is 0. Okay. So now what I'm going to do is the following. I'm going to take a look at this in the following funny way. I'm going to think of one channel as being the channel from u1 which goes to the output y1, y2. Okay? So I have this channel w, remember. This was the channel which took the x to y. And I'm going to create 2 new channels from these 2 uses of w. I'm going to have 2 new channels, which are the following things. Let me call this channels to be, I may need that at some point. The channel, I'll call it W minus channel. Okay. The reason for this minus and subsequently plus will become obvious in a few minutes. So W minus will be the channel that takes from U1 to Y1, Y2. And the channel W plus is the channel from U2 to Y1, Y2, and I should not be writing too low in the blackboard, right? So people are putting up and down. Better now? So, now you might say this is a very strange decomposition. You can understand the channel from U1 to Y1, Y2, and U2 to Y1, Y2. But what the heck is this U1 doing at the output of the second W plus channel? So because it looks like I have created something which is not present at the original output. Let me discuss things for a second before I come back to this thing. So try to explain to you why I can pretend that I have the U1 there. Let's go to the following thing. I'm going to compare 2 decoding strategies. Okay? So one is going to have a helper. So suppose you do this. Suppose you want U2 is sent. Okay. Some observation dependent Z is received. Okay. And I wish to recover U1, U2 back from this observation Z. So in case 1, okay, or in system 1, we're going to have the use of a genie. Okay? So the genie, you know what it is, right? The story, Aladdin goes to a cave, finds a lamp, he rubs it, some genie comes up, okay, and then, of course, I mean, if a normal human being would ask for a genie, something actually that is useful, like, okay, make me happy, okay, find me my life mate, etc. We are communication theorists. We're going to ask for something really stupid, I'll tell you what it is. So here's what you will do. You'll estimate the U1 from this observation Z, using some decoding function P1. Okay. And then when you try to estimate the U2 next, okay, you're going to ask the genie, look, I mean, I made this decision previously about the U1, okay, but can you please tell me now what was the real thing? Okay? So, and we're going to use this, the true value of U1 here, okay, together with this output observation, to decode the value of U2. Okay? So this is the genie-aided communication system, which we don't really have. No such thing is available. U1 is not available at the output channel. But now take a look at the system, which which is the following. This is unaided by the Genie. I'm going to do the following thing. Let me call it to be output to be U1 tilde. So this guy did not need the Genie anyway, so I'm going to use it as it is. Okay. So P1, so far it's okay. And for the U2 decoding, I'm going to use the same decoding function. Okay. But since I don't have the Genie, I'm going to use the output of the previous decoder. Okay. So I've already made a decision on the U1 tilde. Okay, fine. Now let's see about this thing. So if system 1 works, okay, suppose that the system 1 worked in the sense that the U1 tilde hat and the U2 hat were in fact the correct decisions U1, U2. Then system 2 would also work, because the U1 tilde is the same as the U1 hat. So they use the same decoding function. So if this guy was working correctly, so will this. Okay? But if the U1 is the true value of the correct decision, then the thing that you're using here is in fact the correct decision, which is the same as what this guy is using. Okay? So this guy will also be correct. So whenever the Genie-aided system works, so does the, let's say, the standalone system without the help of the Genie would also work. Okay? So hence, what you see is that I can pretend, if I wanted to have a Genie of this particular type, which provides me the correct past decisions, okay, and analyze that system, the Genie-aided system, okay, which is going to be easier to analyze than the Genie-unaided system, okay, and then to say, okay, look, I'm not losing anything. Okay, so whenever the Genie-aided system is working, so is the unaided system. Okay. Because of this, I'm going to pretend at this W plus channel that this U1 is available at the output, because I'm going to decode in the order that from a W minus channel output, I'm going to first decode the U1, okay, and then I'm going to pretend it's correct, okay, and use it at the W plus channel's output. Okay. So that's the trick I want to use. Okay, so far? How come nobody asks anything? So that's did I lose everyone already? No. Otherwise, I'm going to ask people to ask me questions. Okay, so fine. So now we have the W minus and W plus channels. So now let's see in what sense we have this. Why do I put these plus and minus signs? Okay. Now, let me now take this U1, U2 to be IID fair point flips. Okay? So the U1 and U2 are independent of each other, equal likely 0 or 1. Because of this, you will see that immediately x1, x2 are also IID 0, 1. Okay? So the reason, well, the easiest way to see it is the following. This IID point flips will impose a uniform distribution on the binary 2 tuples. Okay. This map is invertible. Okay. Because of this, you also induce a uniform distribution on the binary 2 tuples at the x, which means that x's are also IID point flips. Okay. So, all right. Now let me compute the mutual information under this distribution. Okay. So I'm going to now write down the following thing. I'm going to compute the I of U1, U2, and Y1, Y2. If you take a look at this, this is nothing but the same as the I of x1, x2, y1, y2. Why is this true? Yes, because the u1, u2, and x1, x2 they determine each other, right? This is so this is a memoryless channel fed memoryless inputs. Okay? So this is simply twice the mutual information between x1 and y1. Okay? Let me call this, by the way, the twice IW. Okay. So there's abuse of notation because inside the I, I'm supposed to stick something like the input semicolon the output. I'm sticking here simply the channel. Okay. And by this I mean the following. Take this channel, consider the uniform distribution on its input, compute the resulting mutual information that you would get. Okay. All right. So this is a function only of the channel. I tell you the channel, you can compute me what this number is. So in some sense, what I've done is to expand this thing as a sum, which has to extend a boring sum, namely IW plus IW. Okay? So if I had, it's twice the same. Okay? But now I'm going to do the following thing. I'm going to expand this mutual information in a different way. I'm going to do the chain rule. So the same number here is also equal to I of U1, Y1, Y2 plus I of U2, Y1, y1, y2, given u1. Right? This is the chain rule of information. Okay. So now, and then note the following thing. The u2 and u1 are independent of each other because I chose them to be so. Right? So I can add here r of u2 semicolon u1, which is 0. Because the u1 and u2 are independent, I can add this. If I do this addition and combine these two terms together, get a chain rule, I of u2 semicolon u1 plus this, same as that one. So because the u1 and u2 are dependent, this is the same as the putting the u2, so putting the u1 to the output. So now what do you see? This guy is the input and the output of the channel W minus. Right? So this guy is simply IW minus. What about this guy? This is the input and the output of the channel W plus. Right? This is the I of the channel W plus. So now this, essentially I took 2IW is the same as the IW minus plus IW plus. So, and then note for the following thing. Take a look at this channel W plus. Its input is U2, which is the same as H2. The output contains, in particular, Y2. Okay, so this W plus channel and its output is seeing Y2. So the channel X2 to Y2 is subsumed in this particular channel. So this channel W plus is the channel W, okay, the channel X2 to Y2, and then more things at the output. Okay? So this channel W plus is providing you more things that you would have gotten if you had used the channel W instead. Because of this, the channel W plus is a better channel than channel W. Right? So this W plus, W plus is better than, in whatever sense that you wish to, channel W. At the same time, so this guy is bigger than IW. This IW plus is bigger than IW. But the sum of these are the same as IW itself. So W minus must be worse. Okay, because the mutual information is conserved here, right? So if one of them is bigger, other one must be worse than the IW. So we have that. For the time being, think of this as being the i's are ordered in this particular way. Okay? So this is a sense in which the W plus is better than the W, and then which in turn is better than W minus. Hence the reason for the plus and the minus notation that I've been using. So the plus is good, minus is bad. Okay? So I took the channel W, I created this one. So what you see is the following. I took a uniform population. So I had all these equally yin-yang W's, okay? And I created a slightly, let's say, more capitalist society. Okay? So I made somebody more rich and somebody more poor. Okay? So I've polarized the society a little bit. The original society of W's, they were all equals. Okay? So now I took, and then you push one to the right and the other one to the left. Okay? So that's the, I'm separating these guys. Yes, that was good. Good. So now you see the beginnings of the polarization phenomenon here. Okay? So you have some. So now, what I'll do is the following next. Maybe I should keep this thing around. I might need this.
So you'll have some kind of a lattice of channels or something in the end? I mean, you'll apply this structure?
I'll use this one repeatedly,
right?
Yes, I'll do it
In
again.
the end, you will have a...
I'll have a whole tree of channels.
So there'll be an infimum and supremum element in that sort of
Which we shall see. Okay. But the principle that if you can do something, you can do it again, is a very powerful principle. Okay? So if something can be done, it can be done over and over. It's an important principle which people sometimes forget.
There's a quote, as the gentleman said, if you don't know what to do, keep on doing it.
So this guy I will keep around for a bit more. I don't want to create things. I have learned over the years that as soon as I erased some part of the blackboard, I needed this thing next second because I wrote down the question. I'll try not to erase But first of all, how do we do this again? I said, okay, if you can do something once, you can do it again. But how? So let's now see very quickly how. If you just show you one step and you get the idea. So we had this operation to convert the channel 2 copies of W into 1 copy each of W minus and W plus, right? So, well, I can take another 2 copies of the channel. Okay. So now I have 2 copies of W minus, okay, and 2 copies of W plus. So now, which are these things? So remember that these inputs here are seeing the channel W minus, okay? And these inputs there are seeing the channel W plus. So what I could do is the following. I could take the 2 W minus channels, I can combine them in the same direction. Okay? Right? So now what this guy is seeing is the channel W minus minus. Okay? So, and what this guy is seeing is the channel W minus plus. In this superscripts, read this thing from inside out. Okay, so W minus plus means that I took channel W, I took its minus. Okay, now I have the plus version of the W minus channel. Okay, so this means this. Parentheses move from the inside out. And I do the same thing here. Okay. Now this guy will be seeing W plus minus. This guy will be seeing W plus plus. So now, if we then maybe, if I call these things to let's say U1, and then here, because I combine these things last, I should call it U1, U2, U3, U4. Okay. What you will see is that this is exactly the type following thing. What you'll see is that the W minus minus is the channel from U1 to all these Y's. Okay. Y1, 2, and 4. Okay. W minus plus is the channel from U2 to Y1, Y2, Y3, Y4, and U1. W plus minus is the channel from U3 into the same structure of these Y's. And U1 and 2. W plus plus is the channel from U4, Y1 to Y4, U1 to U3. So, and exactly you will decode them in the same way that I said. You will use these guys to decode U1. Then pretend that's correct, so that then you can use the output of the channel W minus plus to decode the U2 continue on. Okay. So it's the same successive decoding strategy is going to be used here. You can repeat this thing again, of course. You can take the same block diagram, repeat it once again on the bottom, combine things in the same way, and we'll get the channels W minus minus minus, W minus minus plus, W plus minus plus, etc. Okay, so you get 8 channels after this process. All right. Okay, so maybe before I go further, I should give an example of this, what the heck is going on with these W plus and minus channels to get a feeling as to are these getting extremal or not, right? So I claim that this process is supposed to push things to the perfect and the drunk extremes. Let's just give an example as to what actually does happen. For the example, we're going to take a look at the binary erasure channel. Okay. So the channel is this W, is going to be the following. It has 0 and 1 as the possible inputs, okay? Always binary, right? And the output is going to be, again, the symbols 0, 1, and then a special symbol called the E, the erasure symbol. Maybe I'll call the question mark symbol. And then the channel is going to be like this. Okay. So let's say if you send a 0 with probability 1 minus epsilon, you're going to get this 0 symbol out. With probability epsilon, you'll get this question mark symbol. If you send a 1, it'll be again the same thing. Either with probability epsilon, the thing that you send is going to be lost, and you get this question mark at the output, or you get a correct copy of what was sent. Okay? So this channel either duplicates faithfully what was sent, okay? Or it says, look, I don't know, I forgot what was transmitted. This channel. Okay? Now let's see what the channel W minus looks like. The channel W minus is this. Okay? So the input is U1. Okay? And if you take a look at the output, it's the following things. The output is Y1 and Y2. Okay. All right. So Y1 is either the following things. So let me just write these things down. So Y1 is either U1 plus U2, which is the faithful representation of the input to the channel, the top channel, or it is erased. Followed by the second output, which is either the U2 or the question mark. Okay. So that's the 4 possibilities at the output. All right. Now let's see. If you receive both of these things faithfully, if you receive both U1 plus U2 and the value of U2, you can recover U1. So the inputs will be evident if both these channels do not erase. Okay. In the case that no erasure takes place, you're fine. If on the other hand, let's suppose this one is erased, okay? So if the Y1 is the question mark, and then the Y2 is not, okay? Then you obtain the U2, but I mean this tells you nothing about the U1, you're completely in the dark. Okay? So the first channel making erasure essentially kills you. Similarly, if the second channel erases, okay, you have no idea about the U2, and you receive, let's say, perfectly U1 plus U2, but it's also useless because the U1 plus U2 tells you nothing about the value of U1. Because the U2 can be equal like to be 0 or 1. If you get a 0, well, the input could have been 0 or 1, similarly otherwise. Okay? So if either of these things erased, you're completely in the dark. Okay? If both of them are erased, then you know perfectly. So this channel is equivalent to a new erasure channel. So W minus is equivalent to the channel 0, 1 is fed, and the output is either completely recoverable from the output, either exactly recover what the input is, okay? Or you get this question mark symbol. And what are these probabilities? Well, you are faithful only if both of these channels do not erase. Okay? So, yes?
Is the input a vector or just U1?
Input is just U1. Input is simply U1. It's a binary input. Oh, I see. Sorry, I put these dots to indicate what input is. So that is not a 0. Okay? So we erase these dots. So sorry. My handwriting gets, I think, worse with English. So this channel is W minus. So what is the erasure probability? It's the 1 minus this, right? So if you write that down, it is 2 epsilon minus epsilon squared. The erasure probability of this thing. Let me call this thing to be epsilon minus. Okay? So epsilon minus is 2 epsilon minus epsilon squared. If you take out W plus, okay, what you'll see is the following. In the channel W plus, we are lucky because we already know the value of U1. Okay. What you'll see is that if either of these channels transmit are faithful, okay, if either of these W's, original ones, faithfully send, then you're okay. So for example, if the Y1, let me just write this, okay, so W plus, the output input is U2, okay. And the output consists of, again, the same stuff, U1 plus U2 or question mark, U2 and question mark. You also get the U1 for free, right? Okay. So now, suppose this guy did not erase. You know U1 plus U2, you also know U1, you can determine what the U2 is. Right? If this guy doesn't erase, okay, you're set already because you know U2. Okay, so, and if both of them erase, okay, so you only get erasure and U1, which tells you nothing about the U2. So the So this is again an erasure channel. Okay? So this guy is equivalent to a channel in which the again you have 0, but this guy has now epsilon squared is the new equivalent erasure probability. To get an erasure from this stability plus channel, both the original channels must have erased. Okay? So that's the case. Fine. Let me now try to give you a numerical experiment of some type to see where this thing goes. Okay? You can read more on this, right? I mean, it's not that terrible. I don't want to bring down up and down the curtains, should I? Or, it's fine. So now, what I should first do is to write some small scripts, okay, to, for example, it should duplicate, okay, so let's see. Read the input. This is a language called awk for Aho, Weinberger, and Kernighan. Okay, so Kernighan's name is Kernighan Ritchie. Aho, you actually have maybe read his compiler construction books and so on. Weinberger is Weinberger. So anyway, so it's a very nice language. So this says that they take the first item in the line, okay, assign it to the variable e. Let me just print the square root. Let me also print 2e minus e times e. Okay. So to this input, for example, if I type 0.4, okay, you'll get the 0.60, which is the square root of 0.4. And 2 times 0.4 minus you get 0.64. If I give the input, let's say 0.1, okay, you get 0.1 squared, 2 times 0.1 minus 0.1 squared, etc. Okay. Now, what I could do is the following. I could, let's say, something. Let me put this in a small script. Okay. So let me call it in the polarization of the BEC. Fine. The current directory to my executable path. Okay, so, right, so now, if I, for example, then echo 0.4 into this script, okay. So they get these 0.0, etc. Now what I can do is to feed the output of this to 0.60 and 0.64 into another polarization process. So we get now 4 of these numbers. Okay? So this is the 0.4 squared twice, okay, etc. I can do even more. Okay? Nothing prevents me from doing this thing. So now you get 8 channels. Remember, all these things essentially doubling the number of channels that we have. Okay? So these are the erasure parameters of these channels that I'm constructing. Is this okay, by the way, or have I discussed? Let me then do the following thing. So let me stick 2 of these things together. Okay? Just to save myself a bit of time. I think this is hilarious.
This is much observation.
Yeah,
You probably haven't seen it yet.
Oh yes, it is. So this essentially does this operation 4 times. Okay. Now I can do this thing multiple times. Okay. So end up with creating 256 channels. But let me now plot these numbers so you can see what happens. Let me sort the output of this and put this thing into a file. Let me go to the 8 vectors, because 8 is because I have 8 stages, so I create 2 to the 8 channels. 8. Just plot these things so we see what is happening. So what you see is this. Right? So in the x-axis, you have numbers from 1 going from 1 to 256. It's essentially indexing the channels that you created. Okay. On the y-axis, you see the erasure parameter of the channel number I. Okay. And these are sorted from the best to the, from the worst to the best. No, best to the worst. Okay. So what you see is you have a whole bunch of channels, okay, which are almost perfect. The erasure parameter is close to 0. They don't erase. And you have a whole bunch of channels, okay, which are almost useless. They erase almost everything, but for the erasure point is close to 1. And there's some transition in between. There's some channels which are neither quite yang and nor quite yin. So there's some channels which are not quite polarized yet. Maybe about, I don't know, a third of the channels perhaps is unpolarized in this business. So let's try this again a bit more. Okay, let's see what happens if you go
Emre?
Yes.
That looks like a cumulative distribution function. Do you know what distribution is?
Extremely ugly. So there's no, I have no expression for that one.
Okay.
So it's a, we'll come to that one because it'll be important to figure out, at least get bounds on how quickly is this transition happening will be very crucial to understand does polarization really happen or not. We have to get something about it. Okay, so let me now doing online research, whatever you want to call it. So let me take this 256 of these channels, but let me do one more time this 8-wise polarization. This is now 16, I guess, right? So now we have 2 to the 16 channels. Okay. I can sort these numbers over. From the best to the worst. Right. Let me plot this one. So the thing has to read, of course, 65,000 numbers and we'll make a plot of this. We'll take this maybe a second. Here we are. So what you see is that transition has gotten sharper. Okay? So we have these number of not polarized yet channels, or a fraction of them, have diminished. Okay? So as we do this thing more, it looks like something is happening. To convince you that we go one more step, okay, so I'm going to go to 224, but let me go to 220. I can do 16. Polarize that 4 times. Make it into 20. Let me actually do a subsampling of this, so that we don't have to deal with plotting moving numbers. Should take long. It's only computing a million numbers. Here's another 30 seconds and I can plot these million numbers up there. What we'll see is that the transition should get, hopefully, if I did everything right, should get much steeper. Okay. Of course, now once this happens, we have to figure out, I mean, is this really some accidental, the BEC, or, I mean, is it really true that maybe if I go to higher and higher ends, perhaps it will depolarize? How are you sure that as I keep doing this and this more and more, it will get sharper and sharper? I will give you some sort of a proof that that this thing happens. Yes?
Is there anything special about the structure of the code when you're just adding the input of one, this auxiliary variable, when you're just adding them, and that's the link between the two, or?
So, if you want to stick to only a 2x2 transformation, and if you want to remain information lossless, okay, there's only so many things you can do. Okay? So, and in fact, this is the only non-trivial one. So, or is equivalent one, of course, I can add the first to the second as opposed to second to the first, but it'll be exactly equivalent. That's essentially, if you stick to the 2x2 structure, that's the only thing you can do. If you go to a larger structure, namely if you try to combine, let's say, 3 channels at a time, there is nothing sacrosanct about taking only 2 copies of W and then doing this very simple primitive inner code inside it. If you took a 3x3 and then put a primitive 3x3 code, okay, then you had more possibilities. Okay. And there's actually work about that also. I'll tell you at the end of the lecture perhaps a little bit more. Okay, so anyway, so it looks like things have gotten more sharp. Okay, so that's the sort of okay. Good. So now I should tell you that indeed this is something useful. I can go back to the thing, so we'll come back. Okay, so that's the, I'll do more numerical stuff. First of all, let's try to understand why is this happening, and is it? So we saw some numerical evidence, but at the moment you have no reason to believe me, okay, except if you're interesting and then you believe everything on the graphics convinces you. It's a different question, but you should try to see that indeed these eventually most of these epsilon numbers, these created values, are indeed close to 0 or 1. To look at this, I'm going to impose a structure. Let me show it and then you will see why I'm doing this. So, let's take a look at this thing. We start with some epsilon value, 0.4 in this one, in the example that I have done here. From this you create 2 new values, minus epsilon plus. From these you create 2 new values, minus. It actually could be that these things can cross. Actually, let me draw as if they're crossing them. Etc. So, what I'm doing is the following. I'm going to take a look at the, after doing this thing, let's say, L times, L levels. We obtain here a whole bunch of 2 to the L values. Okay. There will be L of these plus times here. So L of these minus times here. You're going to have here 2 to the L of n possible epsilon values. And I'm interested in taking a look at how many or what fraction of these numbers have certain properties, say being close to 0 or 1, etc. Okay. So a fancier way to say this is the following. Let me impose a random variable which is uniformly distributed on these 2 to the L values. Okay. Let me call this variable to be, I don't know, let's say z. So z0 is uniformly distributed on the single sample. So its value is the probability 1 is the original epsilon that you start from. So z0 is 0.4 with probability 1. Now, z1 is going to have the uniform distribution on either this or this. Okay. Right? So z2 can take on any of these 4 values with equal probability, etc. So this is the value zl. Is uniformly distributed on these 2 to the L values. And now I have here in my hands a, if you wish, a random process. So what I can do is the following. I can say, from z0, I can with probability half go up or half go down. to obtain Z1. Okay? So what I can say is this one. So Zn plus 1 is equal to either the plus or the minus of Zn with equal probability. Okay? And this will indeed induce the distribution that I'm after, right? Because if I do this, if I follow this tree by going up or down with equal probability every node, it means that I'm actually having a uniform sampling at each of these levels. So now, what I have is a stochastic process in my hands. Okay, so I have this Z process. Z0 starts from a constant, and then I have these new values. And I'm interested in the following thing. I'm interested, what is the probability that this Z sub L is close to the extremes, okay, to 0 or to 1. So we could take a look maybe to show that these ZLs get close to the extremes. I can take a look at some function of these Z's. For example, let me make a guess, which will be wrong actually, but it's a more obvious guess than the correct one. So let's start with the wrong one even if it's wrong. Let's define, let's say, Qn is Zn times 1 minus Zn. Okay. So you see, Zn's are always numbers between 0 and 1. Okay. And this Qn will become close to 0 if Zn is close to 0 or to 1, and will be far away from 0 if Zn is away from 0 or 1. Right? So this Qn is like this, right? So the Qn being small means that the Zn is close to the edges. Qn not being close to 0 means that Zn is away from the edges. Right? So I could take a look instead to prove that this Qn is small. If that number is very high, close to 1, it means that all my Z's are in fact close to either to top or the bottom, to the plus to 1 or to 0. Okay, so far? It's a ridiculous trick, right? Because, I created some extremely fancy stochastic process out of something very simple. We're just going to say, okay, either we square or we do this double minus square business. Okay? And now I have the stochastic process, etc. But you see, I embedded the question into some behavior of the stochastic process, which is going to be easy to figure out. Okay? So as opposed to trying to trace all possible paths and so on, we're going to simply summarize everything in just this one behavior of one particular stochastic process. It's a useful trick. And in information theory, we make also use of these randomization arguments. This is another such example. All right. So this Qn is a positive random variable, okay? Not negative random variable. Okay? So I could take a look at its expectation to get some idea as to its chance of being close to 0. Okay? If its expectation is small, it must be that the Qn itself must be small with high probability, because if it were not, it would be. All right. Now let's see how things go. So what I need to know is the following. So Qn plus 1 is either equal to the same thing with the Zn replaced by Zn squared. Okay. The plus path. Okay. Or replace the Zn by this guy. If you do that, I guess you get something like this. Okay. So let me try to see what is the expectation of this Qn plus 1 condition on the value of Qn. Okay. What I'm going to try to track is the following. I'm going to try to track the expectation of Qn plus 1 given the value of Qn. Let's try to do this thing on the computer because I don't want to mess things up. I think it's easy to do here. Sorry, I'm not a math lab user. It's easier to do some of these things in more modern computer techniques. I'm getting old, showing my age and what kinds of computing tools I use. First of all, only use Unix. First, might define Q of Z to be Z times 1 minus Z. Let me call it Q plus of Z to be Q of Z times Z. So this is, if you go to the plus side, you're squaring the Z, so your Q is going to be this. And Q minus of Z is, since the Z has become Z minus Z squared, that. So I wish to plot on the y-axis, I want to plot the average of the Q plus and Q minus. Okay. On the x-axis, I wish to plot the Q itself. Okay. Let me now do the parametric plot in this case. So this says T is for curve, so I'm supposed to use T instead of the Z in this case. Okay, fine. So the T range should be 0 and 1. The Z parameter only takes on values between 0 and 1. That. Plot. The x-axis is, he says, Q of Z. Okay. On the y-axis, I'm supposed to put Q plus Z plus minus Z divided by 2. Let me also divide by the value of Q itself. Okay. So I'm now looking at the ratio of the expectation of Qn plus 1 to the expectation of Qn, condition on the Qn itself. He told me I should use in T's, I ignored him, so it's an error. Okay, so if he sees the following, so this expectation of Qn plus 1 given Qn, okay, could be as big as the Qn itself. Okay, so because this curve seems to have approaches 1, right? You see that the max value seems to be 1. It's above 0.75. Doesn't quite do my job because I was hoping the following. What I would have hoped to get is this. I would have hoped to get something like, if it were the case that this one was, let's say, less than, say, 0.9 times Qn, that would then say the following thing. If you keep on stages, you'll be sort of, at the next stage, expectation of Q1 will be Q0 times 0.9. Expectation of Q2 will be 0.9 times 0.9 times the expectation of Q0. I'll get the 0.9 to the n, right? So I would have this would have implied expectation of the Qn is less than 0.9 to the n times Q0. This will become small. I'll be in good shape. And I could have said that the Qn must be small with high probability. If it were not, the expectation would not be this. Unfortunately, we don't have the 0.9, we have the 1. Okay. Okay, so is everything lost? Okay. Well, no, okay, fortunately. The thing is, I'm going to define a new Qn, which is the following. I simply take this one. Take the square root of this previous Qn. Let's try with that. So I should put here the square root of my Q of T. And square root of the Q plus. Square root of the T minus. And divide again by the square root of the Q. Aha. Okay. Now what you see is that the on the x-axis the value of the Q. Okay. On the right, on the y-axis is the ratio of the expectation of the Qn plus 1 to Qn. And you see that okay, it's always upper bounded by 0.8, I don't know, second something, okay, whatever. In fact, the number is square root of 3 over 2. Okay? So it's the cosine of 30 degrees. All right. So now we are fine. So I have sort of the 0.9. So what we have seen is the following. Now, let's do this again. By the way, did I go too fast? So, how many people are still with me? Okay, how many people are not with me? Okay, there are some. So, let me then go back for a couple of seconds to try to tell you what I'm trying to do. So that's even more. I'm surprised how many people are with me. you see, what I'm trying to do is the following. What I'm trying to show is this. I want to show that the probability that the Zn is away from 0 and 1 is small as n gets larger. So this is the same thing as the following. So this is the same as probability that this guy is small with high probability. Because that's exactly because if Cn is far away from, is not close to 0 or 1, this product is going to be away from 0. Only way that this number is small is when this number is so, and this one I'm going to use the Markov fitting policy, okay, to say that this guy is the probability that this guy is, say, bigger than a particular value delta is less than 1 over delta times the expectation of this square root of the Zn from Cn. So if I can show this guy is going to 0 as it goes to infinity, then it means that this guy is going to 0 also. So that's all I need. What I have shown so far is the following. So this we call to be Qn. What we showed was this, at least if you did the computer plot, we showed that a Qn plus 1 given Qn is less than this number 0.87 or whatever it is, okay, times Qn itself. Okay. In particular, if you take expectations once more here, what we have shown is that the expectation of the Qn plus 1 is less than this magic number and the expectation of Qn. Okay. Now, if you iterate this inequality, what you get is that the expectation of the Qn is smaller than Q0, which is a constant, right? It's a actually number between 0 and 1/2 because the z is between 0 and 1. Square root, etc. cannot be any more than 1/2 times this 0.87 to the n. Okay. So 0.87 being a number less than 1, if you keep exponentiating it, you get something going to 0 rather fast. So what you see is that this expectation of Qn is decaying to 0, which means that the probability that Zn is close to Qn is close to 0 is getting exponentially big. Okay. Or exponentially close to 1. Okay. So now at least we see that in the case of the erasure channel, okay, this thing that we saw at the in these plots which look like the cumulative distribution functions, there are a whole bunch of numbers that are close to 0, some transition, a whole bunch of them are close to 1. This is saying that the transition takes place very rapidly. Among the 2 to the L channels that we created, a very small fraction is away from being perfect or from junk. Okay? So the channels that we create are indeed of these extremal types eventually. Okay? So now how can we convert this into a communication system?
Hard to prove this analytically. It's hard to prove this analytically.
It's easy. It's trivially simple. I just don't want to go and take the derivatives of a blackboard. I just trust me that the thing that you can see on a graph, if one just does a bit more manipulation, in fact, this number is square root of 3 over 2. So we then have the following, right? So what we have done is this. We have this 2 to the L copies of this channel WP. And what we did here is the following, okay? We group them first. Why is the screen not so? I think green is the most difficult color to see on the black holes. We group them first 2 by 2, right? And then we group these things 2 by 2, etc. So here I have L stages, okay? And here I have these U's coming into the system. One, two, N of these U's come along, they go through these combining stages. Okay? And then they enter the channel. And now what we have is this one. We have a channel from U1 to all the output, U2 to all the output and the U1, U3 to all the outputs and U1, U2, etc. We have created the channel that takes U1 to N. And what we see is the following. Almost all these channels are either perfect or they're junk. Secondly, we have the following. Remember that the mutual information was preserved in this operation. Take a look at the sum of the I of W minus and the W plus, same as the original. In fact, for the erasure channel also, if you take a look at the average erasure probability, we had this epsilon plus was equal to epsilon squared, epsilon minus was equal to 2 epsilon minus epsilon squared. If you take the average of these numbers, you get epsilon back. Okay? All right. So now, what we have is that these channels have erasure probabilities, okay, whose average should be the same as the epsilon that we started from. Okay? So whatever these numbers that we have here, their average is the same as the original epsilon. But these numbers are either 0 or 1. The corresponding erasure of these large stage channels, we have either zeros and ones. Okay? Their average being, let's say, 0.4 means that the 40% of them are 1 and 60% of them are in fact 0. So if you take the average of numbers, all of which are extremal, and end up with a number such as 0.4, it must be the case that 40% of them are close to 1 and 60% of them are close to 0. Which means the following. If you start with a C of 0.4 here, you'll get 60% of the channels are going to be perfect, okay? And the 40% are going to be complete junk. Okay? So what do you then do? You do the following. On the 60% which are good, you send raw information. You take your data bits, 60% okay, of the block length. Suppose the n was, let's say, 1 million. Okay? You take 600,000 bits. Okay? You send those bits on the good channels. And the bad channels, you send them some fixed information. You arrange with the output, okay? You shake hands, say, okay, I'm going to send the 0 on those channels. Fine? So, and the output guy can then decode the bad channels because he knows. You agreed ahead of time that on the bad channels, you'll be sending a particular value, say 0. Okay? So, when he's decoding the output is decoding the inputs, U1. Okay, U1 goes to a very bad channel. Okay, fine. I see no information about the U1 itself, but I know U1 already because I fixed ahead of time with the transmitter to be its value is 0. Okay. The U2 perhaps similarly, but at some point, some of these will become good. Okay. But the good channels, the input is not known, but the channel is a very low erasure probability, so you recover with. You'll see what they are from the output, okay? Because the output is going to contain the value of the input. Okay. So. The thing is this now something specific to the erasure channel alone, okay? Or is this some general phenomenon? Because I only showed this thing to you with the example of this binary erasure channel. Okay? So what I should convince you is that now this phenomenon is in fact completely general. Doesn't matter what channel you start from. You'll end up with either perfect or completely junk channels if you do this process. Let's see, I would say a few more words as to how complex is it to in fact decode, which we haven't done that. Let me remark immediately on the encoding complexity. So what is the difficulty of transforming these U's into the X's which feed to the channel? We start with these n U values and then n X values. So what you see is the following. There are these L stages. L is the same as the logarithm of the block length. In each of these L stages, you have various plus operations that you're supposed to do. Well, how many there are? Well, in half of these lines there's a plus that I'm going through. So the number of encoding complexity of encoding is order of, in fact, actually will be a complete example. Additions, because I go through block n stages, each of them I need to do n over 2 operations. That's the precise complexity of how to do encoding. So very simple. It's not even n squared. Okay? So in any case, you don't expect to get less than n. Okay? So by a little bit of extra, by paying a log n factor, we can do the encoding. Now what about decoding? Okay? So because in the communication field, it is not the encoding which will kill you. Okay? So almost that's never the case. Okay? It's always decoding which is the hard thing to do, because you see the poor decoder here is trying to distinguish between 2 to the n possible alternatives. Okay? So if you do a brute force search, you'll be in big trouble. Okay? So how do we now do this decoding? Can it be done easily? But I'm told that there's only, I think, 5 minutes I'm supposed to speak more before they have a break. Somebody waved at me from the back. I'm not sure if I should embark on this decoding complexity immediately. Maybe not yet. Let me then do the following thing. So let me try to show you how general this process is. Okay, so not for the erasure channel alone, but also for other binary input channels. Fortunately, by doing this erasure channel, we have seen almost all the mechanisms I need. Okay? So this representation of the counting how many channels are good and how many channels are bad by the stochastic process was a clever thing to do. Okay? And good that we did this in the erasure case because that was easy. Okay? Now we'll do the same thing with the arbitrary case. Okay. Done with the BEC. Binary erasure channel. So now let's take a look at a more general channel W, which is binary input. Yeah, now we're given a channel W, which is binary input, but otherwise arbitrary. So what we have is this. Remember what you're doing. The start of the channel W is, say, 2 copies. Okay? And from this, we create the channels W plus and W minus. This has slightly more mutual information than that one, but the average mutual information is the same as the ordinal W. And now I can start with 4 copies of this, create 2 copies of each of these things, do the same operation to get W plus plus, W plus minus, W minus plus, W minus plus. The remarkably similar diagram I'm drawing here, as the case of the epsilons. Right? And I can start with this one, I go to W plus, etc. I can again do the following thing. I can say, this looks like I'm going to now try to count, for example, how many of these channels, after doing this thing L times, I have these 2 to the L channels that I created. These are these hopefully polarized channels. I'm supposed to check what fraction of these channels are being close to drunk, which fraction are supposed to be close to perfect, which fraction are neither perfect nor drunk. Okay? That's what I'm supposed to do. Again, I can turn this thing into a probability question by saying, well, take a random number of this ensemble of 2 to the L channels. And I can do this again by starting here, okay? And the probability half going up or down. Okay? And if I went up with probability half, I went up or down, etc. Decisions at each node independently. And if I do this process, I'm going to end up at a uniformly at random chosen channel here. Okay? I can call this now a stochastic process, which is channel valued. Okay? So this I'm going to call to be W0. W sub 0 is equal to the given channel W. Okay? Nothing stochastic about this. It is fixed. It is your BEC with erasure probability 0.4. It is your BSC with crossover probability 0.1. Whatever have you. Okay, so the Gaussian channel with binary inputs and noise variance to be 0.6. So at the next stage, I'm going to obtain W1 with probability 1/2 by either doing the plus of W0 or the minus of W0. So this W1 is a random channel. It can be only 2 possible channels, either W0 plus or W0 minus. W2 similarly can be either W1 plus or W1 minus. So now I have a channel valued stochastic process. W0 is equal to W, that's the initial time. And then we have this Wn plus 1 is either equal to Wn plus or W minus with probability half. With probability half. And these decisions that you make are independent of the past decisions. So you make these other choices. And now what we are interested perhaps is the following. I can check, I can ask the following question. What is the probability that the mutual information of this IW is neither close to 0 nor close to 1. For example, it's an integer, let's say, delta and 1 minus delta. Okay. So this is simply saying the following thing. This Wn is simply one of these 2 to the n channels. Okay. So just that we choose one. So this probably is simply just counting. Okay. So this means there's a fancy way to say all these 2 to the n channels, okay, which fraction of them have this property of being mediocre, okay? So neither perfect and nor perfect. What we shall do is to show that this probably goes to 0. So to say that all the channels that you have at the end stage are either very close to perfect or very close to true. Okay? Let me do this thing after the break. Okay? So it's like there's some coffee or something being served. See you soon.